Welcome to Lecture 3, the causal imperative. Now, we've already established that software design is fundamentally about preserving causality, the ability to reason about how actions lead to consequences. We've examined the principles that make causality explicit and the patterns that contain it. Now we confront the hard cases. Now, what happens when causality involves time and concurrency? How do we restore causality in systems where it's already broken? How do organizational structures shape the causal structure we create? Today's argument: causality isn't just a useful lens, it must become our primary design criteria. The question, can I reason about this, should dominate every design decision. Let's explore what this means in practice. Now, the hardest problem in software is when causality involves time. Let's look at a race case example. Now, consider two threads modifying a shared counter. Thread A reads the value, increments it, and writes it back. Thread B does the same. Simple operations. But the causal chain is ambiguous. Did A's read happen before or after B's write? Did they interleave? The final value depends on timing. Same inputs, different outputs depending on when things execute. This is causality breaking down. Cause and effect become probabilistic. You can't reason about what will happen. You can only reason about what might happen. Now, race conditions are the most obvious manifestation, but the problem is deeper. Anytime you have a concurrent modification of shared state, causality becomes dependent on timing, and timing is invisible in code. Now, every concurrency model is basically an attempt to restore predictable causality. Let's look at a few of them. Locks and mutual exclusions force sequential execution. They turn concurrent causality into linear causality. But the cost is complexity of lock ordering, deadlock potential, and performance issues. Async await and promises make asynchronous code look synchronous. You write what appears to be a linear sequence of causes and effects. The runtime handles the actual concurrency. This restores local reasoning at the cost of hidden complexity in the runtime. Software transactional memory treats concurrent modifications as transactions. Either all effects happen or none do. Causality becomes atomic. The system handles conflicts. You reason as if operations are sequential. Message passing and actors means there's no shared state. Components communicate by sending messages. Each actor processes messages sequentially. Causality within an actor is linear. Causality between actors is the message order. Now, just a quick note, the actor model is particularly interesting because it makes concurrent causality explicit. You can't accidentally share state. All causal relationships are message sense. The causal graph is visible in the messaging pattern. Now let's look at another example, that of communication sequential processing, CSP. This is similar to actors but with explicit channels. Processes are independent, channels are the ones which connect them. And causality flows through channels. Go routines and channels implement this model. Now, each of these models has trade-offs, but they share a goal. Make concurrent causality tractable. Turn invisible timing dependencies into visible structure. Now let's look at the fundamental challenges specifically with respect to distributed systems. Now when you extend this across networks, multiple machines, no shared memory, unreliable communication, and independent clocks, causality becomes even more fragile. You can't use locks across networks reliably. Message delays are unbounded. Messages can be lost, duplicated, or reordered. Now, two events might happen in different services. What's their causal order? If they are independent, there might not be an order. They are concurrent. Neither cause the other. This is where vector clocks and logical timestamps come in. They are mechanisms for tracking causality in distributed systems. Not physical time, causal time. That this event happened after that event in the causal sense. Now, the CAP theorem and FLP impossibility results are theorems about causal limits. CAP says that in a distributed system with network partitions, you can't have both consistency and availability. Why? Because consistency requires causal agreements across nodes. When the network partitions, nodes can't agree on causality. You must choose either wait for agreement, which is lose availability, or proceed without agreement, which is you lose consistency. FLP is that you can't solve consensus in an asynchronous distributed system with even one faulty node. Why? Because you can't distinguish between a slow node and a dead node. Without this distinction, you can't establish causality reliably. Now, these aren't engineering limitations, they're fundamental constraints on what we can know about causality under distribution and failure. So, what are the design implications for this? When you distribute a system, you're accepting that causality will be harder to reason about. Now, this should be a conscious trade off. Design for eventual consistency where possible. Accept that different parts of the system might temporarily disagree about causal order. Build compensating mechanisms for when causal assumptions are violated. Make temporal assumptions explicit. If your system assumes A always happens before B, that assumption should be in the design, not buried in implementation details that happen to work most of the time. Now use idempotency and commutativity to make causal orders less important. If operations can be applied in any order and yield the same result, you've reduced your dependency on causal sequencing. Now, time and concurrency will always be hard, but you can design systems that limit how much causality depends on timing. Isolate temporal dependencies, make them explicit, and minimize them. Now, let's move on to the other hard case where you've inherited a system where causality is already broken. You join a team, the code base has been evolving for years. Nobody fully understands it. There's no documentation of the causal structure, global state everywhere, hidden dependencies throughout, functions with side effects that nobody remembers. Your task is to restore causality, make the system understandable again. This is causal archaeology. You're excavating the causal graph from artifacts. Now, how do you start off with this? You start with the external visible behavior. What are the inputs? What are the outputs? What are the observable effects? This gives you the boundaries of the causal system. Then you trace backward from effects. Pick one important output. Trace backward through the code to find what causes it. Map the dependencies. This is detective work. You follow data flows, find where state is modified, and discover hidden inputs. You'll also need to document what you find, draw diagrams, write down assumptions, make the implicit explicit. Even if you can't fix the code immediately, you can make the causal graph visible to others. Look for patterns in the chaos. Systems usually have some underlying structure, even if it's buried. Maybe there's a data flow that makes sense underneath the tangled implementation. Finding that structure gives you the target for refactoring. Now, let's look at some strategies for restoration. The first is to make implicit dependencies explicit. You find global state reads and turn them into parameters. Find hidden service calls and pass services explicitly. Now, this increases parameter list, but it makes causality visible. Try to break cycles. Circular dependencies are causality killers. Find them, break them. This might mean extracting interfaces, introducing dependency inversion, or splitting modules. It's painful but necessary. Add boundaries retroactively. Identify clusters of functions that work together. Draw boundaries around them. Define interfaces. Restrict what crosses the boundary. Turn an amorphous system into modules with clear causal relationships. And finally, test to verify causality. As you refactor, write tests that encode causal assumptions. When I change X, Y should change, but Z or Z should not. Tests become executable specifications of the causal graph. And there might be untouchable parts. Some code is always too risky to refactor. Business logic that is tangled with infrastructure. Nobody understands it, but it works. Try and wrap it, define a clear interface, make the boundary explicit. You can't fix the causality inside, but you can prevent it from spreading. Now, sometimes the causal graph is beyond repair. You've got cycles everywhere. You've got global state that is so pervasive that every function depends on everything. You have temporal dependencies so complex that nobody can predict behavior. This is when rewriting becomes justified. Not because the code is old or uses outdated technologies, but only because the causal structure is fundamentally broken and can't be incrementally fixed. Now, it's important to understand the difference between refactoring and rewriting. Refactoring preserves causality while improving structure. Rewriting rebuilds causality from scratch. Rewriting is expensive and risky, but attempting to maintain an incomprehensible system is also expensive. Sometimes the causal depth is so high that the only way forward is to start over with explicit causal design. Now, the key here is don't repeat the mistakes. If you rewrite, understand why causality collapsed in the original. Design the new system with explicit causal principles. Otherwise, you'll end up in the same place 5 years later. Now, let's talk about organizations and causality. Conway's law states that organizations design systems that mirror their communication structure. Now, let's reframe this causally. Organizational structure creates causal structure in code. Let's look at team boundaries. Now, when you split teams, you create coordination overhead. Teams communicate less frequently and less richly than individuals within a team. This naturally leads to clearer boundaries in the code. Now, if team A owns service A and team B owns service B, the interface between services becomes explicit. It has to be because teams can't rely on informal communication. The causal relationship between services must be documented and stable. Now, this can be good. It forces explicit causality at service boundaries. But it can also be bad. It can force distribution where a monolith would have clearer causality. Now, teams that don't talk produce code with hidden dependencies between their domains. Nobody designed the integration, it emerged organically. The causal relationships aren't documented, they're tribal knowledge distributed across teams. When people leave, that knowledge disappears. The causal graph becomes unknowable. Now let's look at code reviews as a means of figuring out the causality which is there in the code. Code review should primarily ask, can I reason about this change? It should not ask, does it follow our style guide? Or is it clever? Or even, does it work? The question is, do I understand the causal impact? Can I predict what this will affect? Are the dependencies explicit? Are the effects contained? If the reviewer can't answer these questions, the changes shouldn't emerge. Not because it's wrong, but because it's opaque. Now, this requires training reviewers to think causally, to ask questions like, what are the hidden dependencies here? What global state does this touch? What side effect does this have? If I change this later, what might break? Good code review catches causal opacity before it enters the code base. Now, this is a very important aspect of building cultures around causality. Organizations that value predictability over cleverness build more maintainable systems. Cleverness often obscures causality. Clever code does surprising things. Surprising is the opposite of predictable. Boring code has obvious causality. You read it and immediately understand what it does. There's no cleverness to decipher. This is what you want. Now, I'm also a proponent of hiring for causal thinking. When interviewing, don't just test algorithmic knowledge, test causal reasoning. Give candidates code and ask, if I change this, what might break? Can they trace dependencies? Can they identify hidden assumptions? Do they reason causally or just execute mentally? The best engineers tend to think in causal graphs. They see systems as networks of cause and effect. They naturally ask what depends on this before making changes. Our tools show us syntax, types, and call graphs, but they don't show us the causal graph. Now imagine an IDE that highlights all code affected by a change, not just syntactic dependencies, actual causal impact. If you modify this function, these other functions might behave differently. Imagine a tool that detects causal cycles, that warns you when you're about to add a hidden dependency, that makes global state access visible. Now, some of this exists, static analysis tools, dependency analyzers, but they're not mainstream and they're not integrated into how we work. The future should bring tools that make causality first class. Until then, the only thing we have is discipline. Now, in closing, I'd say that software engineering is making systems work, but software design is making systems understandable. Engineering is about correctness, performance, reliability. These matter, but they are not sufficient. Design is about preserving your ability to reason. It's about ensuring that the system remains intelligent as it evolves. Now, this distinction is very important because the industry confuses them. We optimize for the wrong thing. We celebrate systems that work but are incomprehensible. We tolerate causal opacity because it ships. But incomprehensible systems don't stay working, they decay. They become unmaintainable. They trap organizations in technical debt they can't escape. Now, every abstraction either clarifies or obscures causality. Every line of code is a statement about cause and effect. Every design decision impacts your ability to reason. Make can I reason about this your primary criteria. Not is this elegant? Not does this use the latest patterns? Ask, can I understand the causal impact? When you face a design choice, ask which option makes causality more transparent, which preserves local reasoning, which reduces the cognitive load on future maintainers. This is the discipline of software design. Now, if you can't reason about a system, you don't understand it. If you don't understand it, you haven't designed it. You've only made it work for now. Design is the ongoing discipline of making systems understandable. It's causal hygiene applied continuously. It's choosing transparency over cleverness, explicitness over convenience, and clarity over brevity. The systems that last, that scale, that adapt to changing requirements, these are the systems with clear causality. Not because they use the right frameworks or follow the right patterns, but because you look at them and understand how actions lead to consequences. That's the goal, that's the discipline. Design your systems so that they can be understood. Everything else follows from that.